Here we have an infinite set of numbers defined by the expression 16 to the n plus 10 and minus 1, where n ranges over all positive integers. We need to find the greatest common divisor of this infinite set of numbers. At first glance, this seems daunting. How can one number divide every term in an endless sequence? A good starting point is to gather some empirical evidence. Let's calculate the first few terms of the sequence to see if a pattern emerges. This will help us form a hypothesis for the GCD. First, we'll define our sequence as a sub n equals 16 to the n plus 10 and minus 1. For n equals 1, we substitute into the expression. Let's evaluate the power and the product. This simplifies to 16 plus 10 minus 1. Adding 16 and 10 gives us 26. And subtracting 1, we find the first term is 25. Next, for n equals 2, we evaluate 16 squared and 10 times 2. This gives 256 plus 20 minus 1. Adding the first two numbers results in 276. And subtracting 1 gives 275 for our second term. Finally, let's check n equals 3. 16 cubed is 4096 and 10 times 3 is 30. So we have 4096 plus 30 minus 1. Adding these gives 4126, which simplifies to 4125. Let's examine these results. 25. 275 is 11 times 25, and 4125 is 165 times 25. A clear pattern is emerging. Based on this evidence, it's reasonable to hypothesize that the greatest common divisor for the entire set is 25. Now we must prove it. To prove our hypothesis, we must show two things. First, that 25 is a common divisor of all terms, and second, that it's the greatest possible one. Our strategy is twofold. First, prove 25 divides every term, then show no larger common divisor is possible. Our first task is to prove that a sub n is congruent to 0 modulo 25 for all positive integers and. We start with our expression. The key is to rewrite 16 as 1 plus 15, which is ideal for the binomial theorem. This gives us 1 plus 15 to the n plus 10n minus 1. Now, let's expand this term using the binomial theorem. The expansion is 1 plus and choose 1 times 15, plus the sum of all higher-order terms from k equals 2 to n. Let's analyze this summation. The crucial insight involves the behavior of powers of 15 modulo 25. For any k greater than or equal to 2, the term 15 to the k contains a factor of 15 squared. Since 15 squared is 225, which is 9 times 25, it is a multiple of 25. This means that every single term in that sum is a multiple of 25, regardless of the integer value of the binomial coefficient. The entire sum is therefore congruent to 0 modulo 25. Therefore, the binomial expansion reduces to just 1 plus 15 in modulo 25. Substituting this back into our original expression, we get 1 plus 15 in n plus 10n minus 1, all modulo 25. First, the 1 and negative 1 cancel each other out. This leaves us with 15 and plus 10n. Combining the terms with n, we get 25n. And since 25n is always a multiple of 25, a sub n is congruent to 0 modulo 25. This proves that 25 divides every term in our sequence. Now, we must show that 25 is indeed the greatest possible common divisor. Any common divisor must divide the first term, which is 25. Therefore, the greatest common divisor must itself be a divisor of 25. Since 25 is a common divisor, and it's the largest possible divisor of itself, it must be the greatest common divisor. For a different perspective, we can prove this using a recurrence relation. This method reveals the underlying structure more clearly. The key insight is to consider the difference a sub n plus 1 minus 16 times a sub n. This choice will cause the exponential terms to cancel, revealing a simpler structure. Let's calculate this difference step by step. We substitute the definitions of the terms. Now, we need to distribute the 10 and the 16 into their respective parentheses. This gives us two expanded expressions. We can simplify the first parenthesis. After simplifying, we have this expression. Now we can distribute the negative sign. This removes the parentheses. Notice that the 16 to the n plus 1 terms cancel each other out. We are left with a much simpler expression. Let's combine the terms with n. 10n minus 160n is negative 150n. Now we combine the constant terms. 9 plus 16 is 25. We can see a common factor of 25 in both terms. Factoring out 25 gives us the beautiful identity 25 times the quantity 1 minus 6n. This means a sub n plus 1 is congruent to 16 times a sub n modulo 25. Our base case for n equals 1 is a sub 1 equals 25, which is congruent to 0. The inductive step is clear. If a sub n is divisible by 25, then a sub n plus 1 is congruent to 16 times 0, which is 0 modulo 25. Therefore, by mathematical induction, all terms in the sequence are divisible by 25. Before concluding, let's see an even more elegant approach using factorization. We can rewrite our expression by separating 16 to the n minus 1 from the rest. Using the geometric series formula, 16 to the n minus 1 equals 15 times the sum of powers of 16, which we'll call s sub n. Substituting this back, we can factor out a5, leaving 5 times the quantity 3s sub n plus 2n. Now let's analyze the terms modulo 5. Since 16 is congruent to 1, the sum s sub n is just the sum of n ones, which is congruent to n. Therefore, the expression in the parenthesis, 3s sub n plus 2n, is congruent to 5n, which is 0 modulo 5. This means a sub n is 5 times a multiple of 5, confirming that every term is divisible by 25. Now, let's state our final conclusion with complete mathematical rigor. Let it be the greatest common divisor of our set. By the definition of AGCD, D must divide every term in the set. This includes the first term, so D must divide 25. This implies that the only possibilities for D are 1, 5, or 25. We have rigorously proven that 25 divides every A sub n, making it a common divisor. Since 25 is a common divisor, and it's the largest possible candidate, it must be the greatest common divisor. Therefore, the greatest common divisor of the infinite set is 25. Thanks for watching. If you enjoyed this mathematical journey, please like this video and subscribe for more exciting problem-solving adventures.